Hi guys, good afternoon. Can you hear me? And just give me confirmation that you are able to see my screen as well. So we can start now. All right. So okay guys, welcome back to the session of deep learning. So yesterday we started with discussing the artificial neural network, right? So we try to understand that what is it that artificial neural network is made of, how it is similar to, right? How it is similar to the biological neuron of the human brain, and what are the important layers like input layer, hidden layer, and output layer. So then we try to understand history about how is the first model, neuron model, was introduced, and what was the components of this model. So it was only made up of the three things. One is weights, inputs, and the activation. So that's how I understood, and what are the problems with that, and then how they try to come up with the perceptron model, which was adding multiple neurons, and how it started working. And but again, with the perceptron model, it was a problem in the learning, and they have to introduce, like godfather of AI, Jeffrey Hinton. He introduced the back propagation method, right? And because of him, now we are able to use the complex problem. Even after solving the complex problem, the major breakthrough went upon when they started introducing the different activation function, right? So we try to understand that what are the two steps that are happening, how the inputs are taken, and step one, we try to understand it tries to multiply the inputs into the weights, and then it is summing up. It is try to sum it up, and in the second stage it is passing all that value, let's say it's called as y, and through the activation function, and then based on the certain criteria, it's saying whether this output will be produced or not produced, right? So activation function is giving us the function of whether this particular neuron will be activated or not activated, also trying to bring the non-linearity in the data sets, and also it try to give you bring down the values between 0 to 1 or -1 to 1. And we also try to understand that what is the real implication, like whenever we want to rank a movie or so. So at that time, if we are trying to make it on the make the decision on the basis of the reviews, so if certain ambiguous reviews comes in, at that time we will not be able to give a positive negative score, so we have to make a probability. For the sole purpose, we started trying to understand, and we went into detail, like what is the activation function, what are different activation functions are available. And we saw example of the popular activation function sigmoid, and then the ReLU unit, right? Rectified linear unit, and how it works, and how the values are coming, which is the activation function which is used most probably for the classification, and how it is trying to give you value, what is the formula, right? Again, ReLU function has different flavors, like leaky ReLU, parametric ReLU, eReLU, and all their graphs we also seen in brief, right? And we started to understand what is the loss function, why it is important, what are the different loss function available, what do you mean by loss and cost function, what is the difference between it, and then how we can understand that how to calculate the loss. And basis of the classification laws, we use binary cross entropy. If it is a multi-class classification, then we use softmax, right? So we also try to solve what is the loss function which are available for the regression purpose. We were also able to discuss, right, what is Hoover and what. We did not went into the detail, but yes, we discussed that these are available function which you can use. Correct. And then we started with very super important topic, which was optimizer. We could only start with the topic. We did not go into the detail. So let's get started. That try to understand what is optimizer. We said that optimizer is nothing but it gives you is the way how we can optimize our parameter, right? Or adjust the model parameter. And again, we try to understand what do you mean by model parameters is weights and the biases. So right. So weights and biases is the main parameters which we are trying to adjust here. If we know the correct exact weights and biases, at that time we will be able to make the prediction correctly. So optimizer in deep learning are used to adjust the parameter. That's what we understood. But the choice of the optimizer greatly hamper the performance of the neural networks. So how we'll try to understand meanwhile, but we also able to discuss that there are different algorithms available for the optimizers. For the very famous algorithm, which is called as stochastic, not stochastic, gradient descent, vanilla version, right? And along with this stochastic gradient descent, this is also called as mini batch gradient descent and stochastic gradient descent. So what we'll try to do is we'll try to understand one algorithm optimizer in detail, Once you understand the working of this optimizer algorithm in detail, maybe I will try to tell you how it is different from the stochastic and the momentum, right? Moment based, the stochastic gradient descent, and the other algorithms are more or less working as the same, but with a somewhat different functionality, or the aim of the optimizer is somewhat different. So some of you are also asking that what is the best optimizer, how to choose optimizer. Okay, we will try to look at certain condition also, but it is not fixed with what optimizer we will choose. When we'll try to understand what is optimizer, at that time this question will be answered, because when we are talking about the optimizer, what is the main of the optimizer? To find the parameters. And why we are trying to find the parameter? Because we want to reduce the loss. So obviously, whenever you're trying to use any optimizer, at that time, if you see your loss is reduced, that means your optimizer is working fine. So whatever choice you have made with the optimizers are working great. So that's how one of the parameters, how you can assess that whether you have chosen a correct optimizer or not. So without wasting time, let's start understanding the gradient descent. All right, I will close the chat window, guys. Try to understand first, and maybe then I will try to look at the chats if you guys have any questions then. So try to understand how these entire things of the gradient descent coming into the picture. So we understood that why need optimizer in order to find our parameters, in order to again to reduce the loss, whatever loss we are getting. Loss, what is loss? It is the difference between the actual and the predicted value. So if we are trying to concentrate on this slide, and if you can see, this is the pretty picture which is available, which is very popular over the internet. Whenever we talk about the gradient descent, this kind of picture you guys might have seen. This is a 3D picture which they are trying to show. And on the basis of that, they are trying to explain the gradient descent. So let's make use of this picture and even start. First, I will give you overview that what topic this gradient descent algorithm is, and what is the main introduction or overview about this algorithm. We'll then try to understand its working, how it is working. Before even we try to go into like how these things are chosen and everything, try to understand the gradient descent will work in this way. We will have a 3 dimensions. On first dimension, let's say this is the third dimension. Okay, so and this is 0. So here it will be weights, here it will be biases, and this will be error. Okay, so what is our aim? To reduce the error. You have to reduce the error to reach the 0 point. And we have to also, while doing this, we have to choose the optimal value, right? Let's use different color. Optimal value, right? Optimal value of W and B, weights and biases. So it will look like this, something like this. So if you try to reach the minimum point, we'll try to understand what is global minima and why we need this global minima and what kind of functions are available, what is concave, what is convex, and this is convex function. Okay, try to understand the main aim, what we are trying to do here. We are trying to visualize the 3D picture. Why we need this 3D picture is our aim is to reduce the error, and we have to choose this parameter, weights and biases, in such a way that the optimal value I will be able to choose in such a way that it will give me a minimum error. Okay, that is the first thing. So okay, before we even go and start this thing, try to understand that what is gradient descent and how it is coming into the picture. So initially there were 2 functions. One is convex function. I'll try to draw here. Let's say one is convex function. It will look like this. And second one is this is concave and this is convex, guys. Okay. This is the convex function. And here the minima lies at the top. Okay, this is the top point. I'll try to show you. And here, let's draw it in better way. Convex function. Here the minima will be at the bottom. Minima will be at the bottom point. Okay. So let's try and understand that. Here will be the minimum point. What these functions are there? Why these functions are there? If I try to take any 2 points, okay, let's say A and B, and try to draw within A and B, if I try to draw any random function as a function at that time, okay, whenever I try to choose 2 points and apply this function and draw the line between them, at that time, what will happen is in concave function, all the values will be remaining below, right? Remaining below, and in the convex function, it will remaining above. Okay. Similarly, if it's A and B, so that is the basic difference, convex and concave. What we're trying to do is, what is our aim? We have to reach to the global minima point. So if you use a concave function, at that time you have to go on increasing the things, and maybe we have to reach to a point. We have to reach to a derivative, because what we're doing is we are trying to take a derivative, right, of the loss function here. Don't worry about it directly. I will not start with what is derivative by taking, but try to understand that by taking the derivative, we're trying to understand that we have to reach to the minimum point. If we take a derivative in the concave function, derivative will be 0 at this point. We have to increase the things. And for the convex function, derivative will be at the bottom, right? D by dl will be at the bottom. So what is our aim now? Our aim is to reduce the errors. So we have to reach to the bottom, right? Here, we have to reach to the bottom point. So that is why we are using convex function, right? And convex function, whenever we try to find out the derivative will be most probably 0 at the global minima. It is called as global minima, and then global minima will be at the downside. And this approach, this is called as gradient descent, because we are trying to take the gradient. Gradient is nothing but the derivatives, and we are trying to using like the, if you look at this example, we're trying to look at this example. This shape is like somewhat hill, and we have to try to reach the top of the hill. But here, what are AB values? Just the guys, AB is nothing but the random 2 points. If I am trying to take any random 2 points, let me tell you, if I take any random 2 points, A and B, and try to apply this function at that time, right? Between these 2 points, it will look like this hill approach. This kind of shape will be created. That is called as concave. And we're trying to, let's say we're trying to go on the top of the hill, right? Here and here, with respect to DL. A and B value, just for the example, guys, I am giving you, not about the, I am trying to explain you the convex and concave function. That's why I'm telling you, because we need to understand the working of the gradient descent and why gradient descent have chosen the convex function. For that purpose, I'm telling you these things. It has nothing to do with the deep learning, but it has to do, but on the way, not directly. Okay, so here we're trying to come down the hill, right? So that is why the name came as a gradient descent, because we are trying to descend, and gradient is nothing but the derivative of the loss function we are trying to take here. So that is the entire thing, guys, concept behind the gradient descent. So let's try and understand, let's clarify everything and try to understand how the gradient descent things will work. Let's say why we need gradient descent is we need to choose the parameter. What are our parameters are? Our parameters are, let's use the different color for this one. Right. So let me write. This is 0. This is weight. Right. This is somewhere bias. Correct. And this is error. Loss. Okay, this is loss. What we are trying to achieve is we have to find a value of B and W in such a way that we get a very less error or around the 0. So how the usually things happens is, whenever we are saying that we are calculating the loss, which is y hat minus y, actual minus predicted, right? So that is the loss. So whenever we are getting this loss, at that time I have to go back. Guys, I will tell you like how the back propagation happens, but for that purpose, I am trying to tell you what is gradient descent. Once we understand the gradient descent, we'll try to understand then back propagation. Because if we start directly trying to understand back propagation, most probably you guys will not understand what is happening over here. how the weights are getting chosen, right? And that's what I'm trying to explain out here. So we understood already that we have a loss function and we have to choose these two parameter, and we have to use this function which is called as convex function. In the convex function, why you have chosen is because we have to reach to 0 point whenever. Why 0? Because what we want to do is, why I want to make the y and the y hat exactly equal, right? Difference should be 0 between them. So that is how, right? So that is how I'm trying to understand these things, that I have to reach to a global minima point. Clear? Let's try and understand what is the equation through which the weights get updated. So whenever I say that this is my neural network, okay, for the simplicity, I'm just taking one hidden neuron, and this is giving me the output. Okay, let's take another color. This is x1, this is x2, this is x3. Here, two-step process is happening. One is summation of the weights, right? Multiply input plus bias. And in second step, it is passed through the activation function. Let's say z equal to activation of y, because entire term I am calling it as y. This entire term is y. And this is what the two-step process is happening. And then everywhere we have a weights, right? Let me choose a different color for the weight. This is weight 1, this is weight 2, this is weight 3, and here it will be weight 4. So how the process is happening? We are getting inputs like x1, x2, x3. We are multiplying them. Let's use different color for multiplication. I'm trying to multiply them, right? This is what happening. I'm trying to sum these things. This is how the sum is happening, weights into inputs, right? Plus the biases. And on the basis of this activation function, based on the threshold, let's say the whatever value, because activation function giving you value between 0 to 1, let's say it gives you 0.6, then it will be passed to the next layer. Then whatever value coming out of this z again will be multiplied by this weight W4, and then the output will come, right? And let's say output has become as 1, wherein my actual value was 0. So what I will do is actual y minus y predicted minus y, which is giving me huge difference, like 1. 1 minus 0, 1. This is my loss. So I have to understand that I have to remove this, bring down this loss. At that time, what happens is we're trying to move backward. Now I will use different color. So when I saw this loss at that time, what will happen is, again, I have to calculate new weights, right? I have to calculate new values for all these weights and biases. That's what is going to happen. And for that purpose, we are moving back. Okay. For that purpose, we have to move back in the direction where again entire things will start, right? We saw that whenever we trying to move from taking inputs, multiplication, activation function, this entire was called as forward propagation. And this forward propagation, once I get the output, right, after that I have to calculate the new weights. That is what the criteria is. This is how I can reduce the loss. Once I get the predicted output and try to calculate loss, and I have to calculate the loss, and then I have to optimize that. And that's why we are using optimizer, just like the gradient descent item, stochastic gradient descent, RMS proper, something like that. And for that purpose, what we have to do is we have to calculate the new weights. And in order to calculate the new weights, this gradient descent algorithm is helping us. So that is the main purpose. I will rub this diagram now. What we are clear that what we are trying to do is we were trying to understand the new weights. For the simplicity, I am just keeping this diagram here, just to understand that what kind of weight we are trying to calculate. This was W1, this was W2, and this was W3, and here it was W4. Whenever this output was coming, we are getting this output. At that time, this weight was W4. So in the back propagation, how the things will happen is, in the back propagation, right? When we are going back, first weight which I will encounter will be W4, correct? So I have to calculate first value of the W4, and how W4 weight will be calculated. I will tell you the formula. Okay. W4 new weight, because this has become old weight. The new weight will be calculated on the basis of W4 old weight, right? Minus eta. I will tell you what is eta. Okay, minus eta multiplied by derivative of loss function dy, derivative of loss function with respect to weights. And what is the weight we are trying to achieve here is W4. So it will be a derivative of loss function with respect to weight W4. So this eta is nothing but called as learning rate, guys. This learning rate, and the value for the learning rate, I will try to understand again why learning rate is there when we are going into this detail for the gradient descent. And now on the basis of the graph, I will try to explain you how the new weights are getting calculated. But try and understand that whenever we are talking about the learning rate cannot be very high or cannot be very less. We'll try to also understand what is the reason for this learning rate value, and you will ask that what is the optimal value for the learning rate. It should be less, not very less, between 0.01 to somewhere or around 0.10 maybe. This is the range initially which you have to give when you are talking about the learning rate. And again, how I am going to calculate which is optimal learning rate. Same thing, guys. Whenever you tried starting random learning rate, and when we calculate entire our weights and biases, then we try to predict, then we calculate loss. At that time, again, the second iteration will start. At that time, we'll again calculate the new loss. If my loss is getting reduced in every iteration, that means my learning rate is correct. Okay, and my learning rate is correct, and my weights are correct, and my optimizer is working fine. That's how I can understand. Okay, and there is also another way. So there is also another algorithm, let's say grid search CV or random search CV. These are the methods to adjust the hyperparameter, because learning rate is nothing but it's a hyperparameter, right? It's a hyperparameter. This learning rate is a hyperparameter. So we have to choose this hyperparameter. For that purpose, optimal value of this hyperparameter. For that purpose, there are also hyperparameter tuning algorithms are there. Like let's say random search CV and the grid search CV. Okay. I hope now the things are clear. What is learning rate? How we are trying to calculate new weight. Now try to understand when I am talking about the gradient descent, how the gradient descent is trying to come up with the new weights. So what I have to do is try to understand again from this point of view. My main aim is to reach the minima, right? Let me use different color for this one. Okay, and this error brings to 0, and this is weight, this is bias. Now how it is happening, guys? It is very super important concept and very beautiful concept. Try to concentrate what I am trying to do. Okay, first try and understand what is derivative. Derivative means what I am trying to do is I am trying to calculate slope. Okay, I am trying to calculate slope, or you can say is derivative can be considered as what is the rise, right? What is the rise for the run? If this is run, if I am moving in certain direction at that time, how much rise is happening in the other parameter? So this kind of angle or slope we are trying to calculate, right? I'll use a different color. The slope we are trying to calculate, right? So how much is the difference between this run over the rise? Or simple terms, this is how they call it. Or you can say I'm trying to calculate the slope. And let's understand now why we are trying to calculate derivative. Why I have to calculate derivative? Because I have to reduce the loss function. So once I calculate the derivative, at that time only I will be able to get the difference, that what is the difference or angle of difference between the changes which I am trying to perform in this parameter. For that purpose, I am using the gradient. And why I am using this gradient is to reduce the loss with respect to weights. So that's why DL by DW. That's how we're trying to do. Let's go to our graph and try to understand now how these things will work. Let's say this side will be, guys, negative slope, right? This is negative slope and this is positive slope. I will explain you why this is negative slope and why this is positive slope. Okay. So we are going to take a different color. To try and understand, I said that whenever we are trying to, once we do the prediction and calculate the loss function, what I have to do, if I am not satisfied with my projections or predictions which has been done, I have to calculate the new weights. For that purpose, what I have to do, I have this formula, right? If I have to calculate first weight W4, I have to check the new weight minus the learning rate into the derivative of the loss function with respect to the weight, right? And this how it will happen. I will tell you. If this is my initial weight, this is, let's say, W4. Okay. If this is my initial weight W4 and I have to try calculate the new weight, at that time what happened? We are trying to calculate the slope. And let me take a brighter color in order to understand the slope. Hope this point, right? This point I am trying to calculate the slope. Now, so what do you mean by slope? You try a line, right? Try to draw vertical line on that point, and this will give you a slope, right? Let me draw it. This line, everything is red. You try to understand by this black color. Now this point I am trying to draw a slope, and if this slope of the direction, okay, trying to understand if the direction of the slope is right side is going up or below, that's where to see. In this case, it is going down, right? Direction is going down. Right hand side direction is going down. So that means it is towards the negative side. This how, if I choose any point here, somewhere here, and if I try to draw a slope, okay. If I try to draw a slope is nothing but a line. This line, let's say, I'm making it darker for the visualization purpose. At that time, if I try to take a right hand side, it is towards the positive side. That's why this will be positive, this will be negative. Now try and understand what I'm trying to do. Maybe let us clarify everything now. You guys are now clear with the things. And again, start drawing the things so you guys will understand in better way. This is our 3 dimensions. Okay. And within that 3 dimensions, I have to reach to the minimum point. Now this we understood what is positive side, what is negative side. And now I started with this W4, right? I'll also write the formula for W4. New weight equal to W4 old weight minus learning rate eta, okay, multiplied by loss function, derivative of loss function with respect to W4. So this is my formula. I am trying to calculate the new values, and they say here somewhere is my W4. Somewhere here. If I try to reduce the values in such a way and take the derivatives, if my slope is negative side, and let's say this is the minima, right? This is the minima point. I'm trying to denote it here, where I can reach to 0 point, right? And let's say this is 1, 2, this is 4. This is 1, 2, 4. This is going on higher side. 5, 6, and 7. So what I have to do is I have to calculate new weight. So this is my new weight. This is my old weight. Let's say on the old weight, I am not satisfied. I am getting lost. So I have to calculate new weight. At that time, what I have to do? I have to calculate first derivative. If that derivative is positive, let's say if this value of this derivative is negative, okay, derivative is negative. If I try to input this negative value over here, let's say, so this negative and negative will become positive, right? So when I try to decide how the initialization or value will happen randomly. First, I try to take any random weights. Let's say I will take random weight as 0.5 for this one. And then I'm trying to understand whether I have to reduce or increase the weights depending on the slope of the line. Slope, what is slope? Derivative. This derivative I have to take, and I have to understand whether the answer of this derivative is positive or negative. If this is negative, if I try to put this negative value in the calculation, at that time, what will happen is negative will become positive. So whatever my old weight was there, I am trying to add the new weight and try to understand from graphical point of view why we need to add the weight. If I am here, this point, right? This is my old weight, and this is, I told you, this is negative side, right? This is negative side, and this is positive side. If my derivative is positive or negative, in this case, we saw started with the negative. In order to reach the global minima, right? In order to reach the global minima, which is at this point, what I have to do is, whatever value I have taken, this was high value, I have to reduce. I have to come down, right? I have to come down to this point. Let me take again different value, different color. I have to travel this path, right? I have to travel this path. So I can get, by traveling this path below the curve, I can get to this 0 point, right? A minima point, sorry, not 0 point, to the minimum point, because this is the minimum value, my error, because this respect to the error, this loss or error is reducing. At this point, error is 0, because in this direction, this will be my bias and this will be my weight. Getting, guys, what we are trying to achieve and how graphically it is coming down. If I am trying to calculate the derivative's value is negative. If I try to input in this value, so it will become positive. So I have to add this value, so I can reach to the minima, right? So if slope is negative, I have to add, so it can come down to minima level here. And if it is positive, similarly, if I try to input positive value, and the positive negative will become minus multiplication. So I have to reduce the value because I already reached here. Let's say I started at this point, okay, positive slope. So what I have to do, I have to travel the path this way. Let's take this. I have to travel down to this path, right, to reach the minima, right? So I have to reduce the value. So that is how. And when I am saying I am trying based on the derivatives or slope, which is positive, negative, I am trying to reduce and increase. There may be certain steps we are trying to take, right? Certain speed, at the speed of which, let's say we started this with this one, and then now we are trying to reduce. So whenever you are trying to reduce, maybe you're reducing the certain units, right? By certain units you are trying to reduce. So the units or the speed at which you are trying to come down, that speed is called as learning rate, guys. Getting the speed with which you are trying to come down or move from the old value to new value, that speed is learning rate. Now try to understand why learning rate is important. If I take a very high learning rate, now let me denote this in greater color now. If I take a very high unit, what will happen? Maybe I will try to reach here, 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 here. Very fast movements will happen. And within that movements, I will not be able to reach to minimum level. And if I take a slow, let's say, if I take very less rate, right? Very less rate of the learning, value of the learning rate. At that time, maybe in order to reach from this red dot to this black dot, I will take several iterations. It will take time, right, to reach this one minima point. So that is the problem again. I cannot keep my learning rate very slow. I cannot keep my learning rate very high. So that is how, guys, getting what is gradient descent, how visually it is trying to calculate new value, and what is the formula for calculating the new value, right? W4. Similarly, the same way, if I choose a learning rate, take the derivative with respect to the loss function for whatever weights we are trying to calculate, and depending on that, we try to reduce the error. Main purpose is to reduce the error. For that purpose only, we trying to act in the different iteration, different combination of the weights, learning rates, and the derivatives at every iteration. And by this, we are trying to identify the weights. This was one example. Similarly, we will have a weight 3. So for same weight 3, I can again do the same thing. And this gradient descent, guys, by the way, this gradient descent is working for entire data set. It is trying to take entire data set combination, then try to work it. That is the main understanding behind it. What is the loss function the SGD followed? Okay. Loss function, loss function is, guys, not related with the optimizer. So it is not with the optimizer, it is with the problem you are trying to solve. If you are using a regression problem or you are using a classification problem, accordingly we seen yesterday, if it's a classification problem, it's a binary class, then we are taking most probably the sigmoid function, activation function, and then we are taking binary cross entropy. If we are taking the multi-class classification, at that time maybe you are using sparse cross entropy function, and along with that you are not using the sigmoid function, you are using the softmax function. So again, depends on the type of problem you are trying to solve. You have to take the loss function. It is not fixed, right? It is fixed as per the problem use case you are trying to solve. If I am using the regression problem, I can take simple N1 loss or L2 loss. The way it works is according to the business case which you are trying to solve. That's why we yesterday discussed, right, what kind of loss functions are available and where to use them. I hope this answers your questions. Okay. So again, what we're trying to discuss is, understand different color. So when I calculate similarly weight 3, again I will doing same thing. New weight will be, let's take a darker color. I think this formula will be visible. Again, when I'm trying to calculate new weight for weight 3, it will be based on the same thing, that weight 3 old weight minus eta. Okay, this is eta multiplied by the derivative, which is derivative of loss with respect to derivative of weight of W3. Clear, guys? Now you understood how the gradient descent is working. I think now from visual point of view and from the formula point of view, and this process will work for all the weights. That's how all the weights will get updated, guys. I think, yeah, I can understand this is very heavy thing to understand. In first go, you'll not be able to understand, but I made all possible efforts to show you from both mathematical point of view also, and also from the graphical point of view also, in 3D, how they are trying to achieve. And we also saw that why we are using convex function, and using convex function, whenever you try to take the derivative slope, depending on the value of the slope, if it is positive or negative, we add or minus the weights from the previous weights, and then we try to take the new weights, and along with the new weights, will again the entire cycle will keep on performing, like going from forward propagation, then taking the inputs, then making the prediction, and then coming back. This entire cycle is called, with back propagation, is called one epoch, and there will be multiple epochs happening. So I think now you guys are very well aware that what is happening in the back propagation, how the weights are calculated, right, and what is gradient descent. It's a really beautiful concept, guys, because this without this back propagation, it is really impossible to learn for any neural network, right? So that is how the optimizers are working. And I hope you guys understood the concept. Just take a quick recap. Okay, I will try to explain again what is happening. These weight initializations or changes happen automatically. Yes, these changes happen automatically. You don't have to calculate every time. So that is the beauty, that whenever we I will go in next slides. At that time I will explain you that how it is happening. I will try to create a perceptor model, and that I will try to explain the iteration. Okay, but this is happening automatically for your information. So let's try to revise the things. Try to reverse whenever I am saying the back propagation of gradient descent. In gradient descent, what we are trying to do, we are trying to find out the optimum value of the weights using this formula. If my weight is W4, which was the last weight, right? Whenever we try to, okay, let me draw simple neural network. Just like this. And here was the W4. This was hidden layer, correct? And this was, let's take different color. This was W1, this was W2, this was W3, and this was W4. And so we just looked at only one simple weight, W4. And again, going back, it will go from W4 to W3, W2, W1, and you try to update all the weights. That's how the back propagation will work. Back propagation will work. And this is a formula through which you try to calculate why we need a learning rate. Learning rate helps you to take the steps to reach the minima point. And if it's depending on whether your derivative is positive or negative, you try or remove from the old weight, and then you calculate new weight. Again, you perform all the iterations. So, and why learning rate is there? Why we have to take learning rate go fast or very high value or low value? Because if you take very high value, it will keep on rotating randomly, jumping from positive slope to negative slope, and it will not reach the minima point. Okay, this is the minima point which you have to reach, where the error or the loss will be most probably approximately zero. So that is our main aim, why we are taking all this pain to reduce loss. And that's how these things will work. If you try to take very less weightages for the learning rate or less value, even to reach to that minimum point, it will take several iterations. That many times the network has to perform the calculation. And if you take higher weight, maybe it is a chance that it misses this minimum. It will keep on hovering between somewhere positive to negative, positive, negative, positive, negative, positive, negative, and maybe it will try to miss these points in the early iterations. Where is the connection between weights while going back and updating the weights? Where the connection between weights? The connection is there, guys, right? So connection will remain same, like connection in formula. This is the formula, right? Connection, like if I try to update the new weight, I am taking old weights. And through this, I am trying to update the weight. That is the connection, guys. I'm not able to understand. Can you just ask in detail, like what part you are missing? What is my aim to calculate new weights? For that purpose, I am choosing old weights, learning rate, and taking the derivatives of the loss function with the weights. That's the connection, guys. How to update weight 3 using weight 4. Okay. So that will try that will come to the next slides. That is called a chain rule. Okay. So what a chain rule is, whenever we try to come back to weight 3, right? At that time, we have to also consider the weight 4 as well as the weight 3. That concept is called as chain rule, that we'll try to understand. But I just at this moment, I'm trying to give you just the idea of the gradient descent algorithm, how it is working visually, and how the first weights are calculated. Just for the example purpose, I given here weight 3 will be again the same formula. The formula will remain same, but this derivative which you have seen here, this derivative will be further bifurcated in this way. Derivative of loss function with the W3 will be written somewhat else. Like it will depend on the previous layer output. Let's say I can write this same formula like d by dl of 3 can be written as d by dl of the output of 3, last output, multiply by, again, let's say this multiplied by output 3 and divided by again this weight of 4. When I am trying to calculate weight 3, weight of 4, and again there will be some addition. Okay, that's how it will come into picture. But we'll try to see that in chain rule when we are trying to understand chain rule. Because in chain rule, whenever we are going back, we have to also consider entire path. Like first it will update the W4, then it will try to go to W1, W2, W3, and while going that, it will follow a chain rule. That chain rule, it is called a chain rule. And using that chain rule only, try to consider the previous weights updation. Along with that, a derivative of the previous weights, along with the derivative of the current weights, and that's how the entire derivative will get added with the learning rate to the old weights. Just for the overview purpose, we'll go in detail. But for the moment, guys, is this clear how gradient descent is working, and what is the formula for updating the weight, and what is happening in the actual process happening in the back propagation? Just quickly ping me, guys, so I can understand that you guys understood this concept. We can move ahead. This was the simple structure. We'll try to understand the chain rule. At that time, we'll taking the multiple weights together. Hope this is very interesting, right, guys? And you understood the concept that how the gradient descent is working. At least one simple way how it is calculated. Yes, couple of more people, if you can give me confirmation that it is simple, clear now. So you guys understood how this gradient descent is working. Couple of more yes, no, guys. Or has it gone way above your head? Or am I confusing? Only two people are saying yes. What about others? Yeah, yes. Reducing. Yes. Reducing. Yes. Okay. What else, guys? Just quickly give a confirmation. So without wasting time, we have to understand many more concept. Explanation is too good. Okay, thank you. What else, guys? Any other thoughts? Just quickly ping me so we can go ahead then. Or any doubt like what is happening over here? What is back propagation now? Why weights are getting calculated here? Few more pings, guys, and then we can move ahead. At least I can get a feeling that everyone is trying to follow and they're on the same page. So we can, without wasting time, we can go ahead then. We have to understand very super important concepts, guys, going forward. So quickly ping me within a minute. I will wait for 1 minute and then we can go ahead then. No reply will also, I will take this as this, huh, guys. All right. All right, guys. Okay. So let's move ahead. I think no one is having any issue, so we can move further. So now we were able to understand what is gradient descent and what is optimizer. And within that optimizers, okay, these are the optimizers which are available. Like I told you, let's try to understand here only. So before we move ahead. Okay, thank you guys for the confirmation. So I told you that gradient descent is one of the optimizer. It is a vanilla flavor optimizer. Out of that is also called as stochastic gradient descent. And then also mini batch. Mini batch. Mini batch gradient descent, GD. So what is the initial difference? Let's try to understand this way. And when we are talking, whatever we have seen the gradient descent algorithm, at that time, it is trying to try to calculate this entire iteration with the entire data set. Trying to take the entire data set and then it trying to perform this optimization weights and everything. So that's how happening in the vanilla flavor. In mini batch, what is happening? In mini batch gradient descent, they're trying to track the data in the batches, different batches. Okay. If you have 100% data set, then maybe they try to take within the 30%, 30%, 30% data set in one iterations, and then trying to calculate all these iterations, everything. So that's how the mini batch gradient descent is there. Again, there are pros and cons, like why we are doing it. Maybe let's imagine calculating all these calculations. You understood we have to calculate derivative each and every point for all these many epochs. Let's say if I'm doing 100 epochs at that time, they trying to learn. So all this data has to move forward, move back, calculate those many connections, how many connection of the weights are there. And data has to continue like for hundreds epochs, 200 epochs, and so on. So imagine kind of, let's say, kind of resources it is using or kind of time it is taking to perform the calculation is also possible. And we'll try to understand even when we are trying to go into further details at that time. What happening is when you're having a very depth of these hidden layers, at that time, you may face a vanishing gradient descent problem. So don't worry about what is vanishing gradient descent. Vanishing gradient descent and exploding gradient descent is the issue which you will also face. And we'll try to understand this concept when we go further. But this kind of issues will also follow, and we have to also take care of this kind of issue, and why these are happening, we'll also try to understand. So imagine the competition it requires, imagine the iterations is trying to perform, that many derivatives it is performing. So for that purpose only, they have come up with different algorithms for these flavors. And this specially adaptive moment estimation and some other things. What they are trying to do is they're trying to also understand, trying to take a concept of the moment, right? Momentum. They're trying to produce the concept of the momentum in the calculation of this optimizer. So even SGD, that is stochastic gradient descent, with momentum is also there. Okay. And the Adam optimizer is there, which trying to bring the Adam. This Adam optimizer is there. Is trying to introduce the concept of the movements. Okay. So what is the concept of the movements is, let's say, you guys, if you remember, let me draw the diagram for the stochastic gradient descent. Maybe you guys will be able to understand that. My stochastic gradient descent is different. So what we're trying to do is using the normal gradient descent, this stochastic gradient descent. Stochastic gradient descent and some other descent algorithm, what they're doing is they're not taking entire data set at one point of time, right? And this is minimum point, let's say. This we're trying to reach, because we will reach minimum point, the loss will be less. So what happening is in gradient descent, we are taking entire data set and by slowly as per the learning rate, right? Using the learning rate slowly and in a, let's say, organized manner, we are trying to reach the minimum point because of the learning rate. But in stochastic gradient descent, what is happening? We are trying to take the data in the iterations, right? There are different iterations. And in that iterations, we are trying to take the batches and other data. At that time, what is happening is there will be noise which will be created, right? And this will look like this. And after handling with this noise, it will try to converge to the minimum point. That is the basic difference. Let's say if I draw like this one. Okay. And this is the initial weight, and this is the point which we are trying to reach. What will happen initially if I take learning rate, small learning rate? For gradient descent, entire data set is there, so we can reach slowly. But what happens is in stochastic gradient descent, we are trying to take the data in iteration, so it is moving from here and here, small changes of the derivatives, and that's how it is taking time. So that is one of the difference between the stochastic gradient descent, the gradient descent. Also, this we are taking time and we are taking batches, so it is creating noise. Based on that noise, again the derivative slope will be different, and that's how it try to converge. So it will take time to converge. That is again a problem with the stochastic gradient descent also. So what I was trying to tell you that when we are trying, stochastic gradient descent is also can be considered with the momentum. Momentum means what? Momentum is we're trying to take the account the let's say time factor here. So let's try to understand in this way. So if I have a data, okay, let me try and create one data for you guys. Let's try to understand the overall real idea behind the stochastic gradient descent with the momentum is that what we are trying to do is in stochastic gradient descent, we saw that we are taking the data in the batches, so it is creating a noise. Yeah? So this is not smooth, guys. It's not smoothly trying to converge. So there is a lot of noise and variation which is happening. So what we're trying to do is we're trying to use the method of the exponential average. Exponential average. Even in the time series, no need to tell you guys, in the time series method, when there is not a stationary data, we're trying to bring it using the exponential average smoothing, right? We're trying to smooth this data. Whatever this path is going, we have to create a smooth convergence, right? Smooth way. So for that purpose, we are using the average exponential average method for the smoothing, and that's how we're trying to reduce the average. So what happening is here, clear everything. Let's say I have a data here, time T1, T2, T3, T5. At that time, my weights biases will be like this: B1, these are my data points at that time, B2, B3, and B4. Let's say this is 4. Okay. What is happening over here is when I'm trying to calculate, let's say VT, that is this first one, VT1. Use chart. When I'm trying to calculate VT1 with respect to this, right? So what is my formula again here? What I have to calculate VT1 is value is B1, right? Try understand guys, and I'll try to make you guys understand better first. My first value at the point T is B1. When I'm trying to calculate value at this point 2, right? Time 2 will be VT2. And how I will be able to calculate this? By the factor gamma multiplied by V1. V1 is the previous one, right? V1 plus B2, right? Plus B2. So this gamma factor I will introduce. Because moving from time here to here, if I have time to calculate B, I have to also consider the reference to the previous time, right? So that reference is called as momentum. I'm trying to bring the momentum in the calculations, right? So for that purpose, I use the parameter, which is look like this one, gamma shape. And this value of this gamma is between 0 to 1. Okay, value of this gamma is between 0 to 1. So let's draw this again with better color. So when I calculate the V1, I can directly say it's a T1 value at let's say value at T point T VT1. So it is directly V1. But when I try to consider as at time 2, it should be the combined effect of the previous time and the value at that time, right? For that purpose only, what we are trying to do is we're trying to introduce the variable gamma multiply by V1, right? And plus the value which is available B2. So this by introducing this gamma, I'm trying to introduce the momentum, and this value is between 0 to 1. So introducing this gamma factor again, I can understand that, and why we are introducing that this factor is whatever recent value is there, B2 will have a more weightage, and this, let's say I told you guys that value of the gamma will be between 0 to 1. So how the value VT2 will look like is, if I try to insert a gamma value as 0.5 multiplied by V1 value plus the directly B2. So try and imagine what I'm trying to do here is for the value which is the previous value for the time, I'm giving less weightage, and for the value here which is the current value, I'm giving higher weightage. But somehow I'm trying to give a reference of the previous time also, right? Previous time also I'm trying to that is concept of giving reference is called as momentum, and because whatever the value at the current stage will be depending on the values of the previous stages, right? Simply from the science point of view, right? So that's what the concept we are trying to bring it here in while calculating the stochastic gradient descent. That's a simple concept. I don't want to go into mathematics now because it will cover at least 1 hour to understand each and everything. But just to give you hint that when I'm saying that I'm trying to take the HGD, that is stochastic gradient descent moment. So what I'm trying to do is, even when I try to calculate this value of 4, I will try to calculate the effect of this T3, T2, and T1. So how it will look like is VT4 will be also product of what? Gamma. Second derivative is a point of concentration. Yes, we can say that, but what I am trying to do is whatever values which are related to previous one, we have to give a less weightage, and whatever derivative at the current stage we are giving more weightage. That's the only thing they are trying to introduce here. And I don't want to go into detail even. I have to even to make you guys understand each and everything. Even I have to come prepare one more like 1 hour session. So just I'm trying to give you from the basic point of view that whenever I'm trying to calculate value at the time 4, it will be a product of, let's say, gamma into T3 plus gamma into T2 plus gamma into is there like B4. That's how. That's how it will try to calculate, and based on the value of 0 and 1, it will try to give the weightages, and then it will calculate the final value of VT4. Because what we are doing is we're trying to take the value of consideration to the previous movement from previous values as a reference, and that is called as introducing the momentum. And why we are trying to introduce the momentum and all? Because we are not taking entire data set, taking the data set in various, let's say, iteration at that time. It is not smoothly converging. It is like zigzag pattern. To bring this zigzag pattern in a smooth curve, we have to use these momentums. So that is the only things we have to consider. We don't have to go in detail, because all these things are happening already automatically using the, whenever you say that I am using stochastic gradient descent as my optimizer, all these things are happening automatically. But why I am trying to tell you that you guys should understand that what is happening in the background, and how it is trying to converge to the global minima, how we trying to reduce the things to the minimum level. That is the main purpose to tell you that you should not tell tomorrow that I have not told you what is the background information about how the gradient descent is working, how the gradient descent of the vanilla flavor, which is bringing momentum and all, what is happening, and why is it is important to bring the concept of momentum and all. So that is the sole purpose, guys. I hope now it is clear. So let's, because I thought we'll create one artificial neural network today itself only. So I will make a walkthrough, and I will try to create one artificial neural network. Before that, we have a couple of more important topics to understand, like what is the problem when we try to train our neural network with the less weights or more weights, or how the sigmoid function is creating issues whenever that is going. That topics like vanishing gradient descent or exploding gradient descent. Again, what is the dropout layer? Because we need a dropout layer also. This is 3 important concepts, guys, we need to understand. Then only we will be able to understand the entire picture end to end, like how the weights are updated. Even the chain rule is also important, like sir was asking, oh ma'am, I don't know. Someone was asking like why how the connection between weight 4 and weight 3 is. Then when I'm trying to update weight 1, whether it will try to take into consideration the previous sets or not. That is also we need to discuss quickly. So I hope things are clear, guys, and I've put in these slides to understand. No need to worry about it. But I will read a couple of points which are very important. Like what this says is gradient descent become when the how to choose the optimizer is based on the data, whether data is sparse or not sparse. If data is sparse, what do you mean by sparse? Means it has a lot of variation, lot of noise in it. At that time, we can go for the Adam optimizer, because why? Again, told you the same things, right? So in order to reach the minima level, it is going like this, not smooth. So we have to make exponential smoothing and all that thing. So for that purpose, we have to introduce the concept of moments and all. So for that purpose, if, depending on the data sets and the type of variation or kind of business problem you are trying to solve, we have to take these things. And what Adam is doing is trying to add the bias correction and momentum, right? I told you bias correction and momentum on the basis of RMS fraud. Forget about RMS fraud. It is root mean square proposition. Will not go into detail. Again, it is a different optimizer. Try to understand this way and working on certain other criteria. So Adam is the best optimizer. Some of people says, because whenever the data set is tried to variate with the various noises and it's sparse, so smooth conversion is not possible. So momentum, introduction of some momentum, very important concept. Or even you can introduce the HGD with the moments. With the moment, this is also the optimizer which is available, HGD with the moments, and many paper they are using HGD only, okay, without momentum. But and even for the initial neural network, artificial neural network, for the initial level, for very simple topics like machine learning algorithm, where we're not trying to make a very vast complex decision making. At the time, we are using only gradient descent. Gradient descent only, not even stochastic gradient descent. We are trying gradient descent vanilla flavor, or maybe the some flavor of the mini match gradient descent or stochastic gradient descent without even momentum. Okay. So even though stochastic gradient descent can reach a minimum value, but it takes longer time, that we explained, right? Try to understand that why it try to get trapped in the saddle point, because all of a sudden it cannot go to the minimum point. It keep on moving like this because of the noise data, and to reach this, it will take many iterations. You will say, what if I increase the learning rate? Because we saw on learning rate also, so it will move like this only, this kind of zigzag pattern, even if you introduce higher rate of. So that is the main things that why should we choose or what not choose. You can go again in detail, but nothing much to discuss about these things, but mainly depending on the data, whether it is sparse or not, and whether we are trying to deal with the exponentially smoothing or not, or reference to the previous data, we are using SGD with the moments or without moments. And then we try to understand that what is the issue with the SGD with the moments, if you're trying to take a more time to converge to the to the loss function to the minimum point. So it's not like that it will not reach, but it will take more iterations. So that's how. To faster convergence, whenever we require faster convergence and more complex neural networks are 10, at that time we are using the ADAM. Okay, so that's why they are saying ADAM is best. That's how, guys. So let's move to next topic. So this now I thought first we'll try to understand optimizer, and then we'll try to understand how back propagation is happening. I guess we already discussed that how the back propagation is happening. What happens in the back propagation now, everyone is aware that input layer, we are going from the hidden layer where summation of the weights is happening, multiplication of the input with the weight. Then in second step, activation function get activated. That is called as Z. That is happening. That entire Y is passed to the activation function. Then whatever output comes in, that output is again multiplied by newer weight, and that's how the output will come, right? Once the output comes in, again then we have to calculate the loss. Let's take different color. We have to calculate loss, and for that purpose, for the simplicity, I am taking loss as like y hat minus y actual minus predicted, and based on this loss, again we have to choose the optimizer. Again, optimizer, what it will do, it will try to calculate the gradient of the loss function with respect to the weight you are trying to calculate. Let's say here is the W4 first, and then going back to this second layer. Second layer, this is, let's say 1, 2, 3, 4, and this is somewhere around like say 5, 6, 7, or 8. And again, this kind of the iteration will happen. Okay, it will go on, and when we trying to calculate this weight, okay, this weight has a connection to the previous weights, because in order to reach this weight, I can take two paths, right? This path, or I can take also this path. So at that time, we have to also consider the loss function for this weight, loss function for this weight, and all loss function has to be added along with the loss function for, let's say, this was number 3, right? So whenever I am trying to calculate the loss or new weight, let's say weight 3 new, at that time, I have to consider the loss function, or let's say weights for this one, also this layer, this old value minus eta into the derivative of with respect to 3, and this 3 will be further will be product of all these two weights and the derivatives of the loss functions. So that is how the things will happen. So that is called a chain rule. We try to understand going next. What is chain rule? Hope this process is now clear. I just for the information I have put in this guide. And I told you like the back propagation uses the chain rule to improve the output. Basically, each forward pass has a through the neural network performs backward pass also, right? And try to adjust the weights. At that time, whatever weights are available in the earlier layer, let's say two hidden layer, we have 2. And for the calculation, the first hidden layers weights, we have to also consider, because we are going from the backward direction. We are going for the backward direction. So first we'll encounter layer 2, then we'll go into layer 1. So we have to also consider the previous layers weights as well when going to next layer. So that is what the chain rule says. Try to understand this again, the same thing, guys. Just I try to draw these things so you guys can understand the calculation, but quickly I will finish this up. So this is what is happening. X1 is coming, X2 is coming, X3 is coming. How we are training the single layer neural network. That's what the example is here. And here that two-step process is happening. 1 and 2. Step 1 is this one. Step 2, pass to activation function. Then activation function, this Z will be multiplied by W4. And this is how, based on the probability criteria, right? If more than, let's say, threshold, if more than that, it will going to give you a Y hat. Okay. Try to understand this way. Now, what is Y hat? Let's say it's 0. And what is Y actual is 1. So what I have to do is, whenever I got this prediction, I calculate the loss Y minus Y hat. And why I'm squaring for the simplicity purpose, so I can understand. If this if loss the predicted value is very high, so maybe this particular value we will get less. For that purpose, we are trying to calculate the loss, squaring the loss. And then once we square the loss, what we're doing is calculating, going back, and let's say in this case we are trying to calculate the weight, new weight. Now we are using optimizer. Optimizer, what we're trying to calculate using same thing, same formula. Just for the recap, I am telling you guys that W4 old minus or plus, which we also saw how it is getting based on the differentiation derivative with respect to weight 4. This is what is happening currently in single layer. When we move further, we'll also try to talk about the W3, W2, W1, but the formula will be same. Like if it's W3, it will be like W3 at that point plus W3 or old weight, new weight will be old weight minus learning rate into product of the let's say multiplied by the loss function with respect to the W3 loss weights, right? And that weight, whatever that particular calculation we're trying to consider, we have to add some more products that we'll try to understand going forward. But I hope this how the process is working. We also saw the example. I tried to put in some example that if you guys are trying to play for 2 hours and study for 4 hours and sleeping for 8 hours, then what is the probability that you pass the exam? So that can be solved easily. So that's why it came as 1 or no or loss, and then we try to calculate it. So I understand when we are having a complex neural network, let's say more than one layers are there. At the time, how the process is going to work is, these are the output 1, output 2, right? And this is the final output. And this is output. This is like output layer, hidden layer 1 and output 1, because we are getting first input, first connection and passing to the first neuron. That's why 1. This is 1, 2. And this is 1, 3. And whenever we are trying to pass these inputs to the neuron, there will be a matrix calculator, weight matrix. How the weight matrix will be calculated? Like if I have a 4 input, and then for these 4 inputs, I am passing this 4 input to the 3 neurons. So 4 multiplied by 3, that will be the weight matrix it will have at this layer. And then when we have this output from these 3 nodes, and we'll go to the next layer, because next layer we have a 2 neurons. So at that time, it will become 3 weights multiplied by 2. And then we're reaching to the next level before the output layer. At that time, we will have like 2. These are the 2 weights which are going and getting multiplied to the 1 neuron. So that's why matrix will be 2 into 1. That's how. First hidden layer should have 6 outputs. Why it should have 6 outputs? I'm not getting. I will try to explain you guys why it has these many outputs. Even though I have, let's say, it's not like that 4 into 3 or some calculation is happening. This is depending on, let's say, depending on the neurons. In this case, from each node to no, that's not happening. That's not happening. Let's say I'm just trying to consider. Okay, so you are saying that I've given a connection, two connection from each. That's why you are saying output. No, not like that. So what happens is when what happens is X0 will go here, X1 will also go here, X2 will also go here, and X3 will also go here. Okay, and all this summation will happen of X and weights, and then it will be called as Y. plus some bias, right? So that will be passed to the activation. So that is called as Z, activation of Y. That is Z. That is a unique output. Okay, that's Z. So that's why we have only one output here, Z. That Z is going now to this layer as well as to this layer. That's why there is only one output. Output in that sense we are talking about. When we are trying to pass all the weights in step 1 and step 2, we're trying to then how the weight sum occurs, for example, F22. Okay. For F22, what will happen? Okay. Weight 22, what will happen is, if I am for F22, whatever weights are there, let's say these are the weights, right? Let's say this one is going here, this one is going, and this one is going. For that respective weights, we have to multiply the Z's. Only one input is there. Let me clarify. F22. We are getting multiple inputs, right? From here also we are getting, from here also we are getting, and from here also we are getting three. We are getting three, right? So three, and this will be, let's say, weights at the layer 1, layer 2. It will be at like weight 21, weight 22. This is weight 23. 2 for the second layer. This is first was the input, and then the first node, second node, and third node. That's how it will happen. I hope this answers the questions. So let's try to understand further. So when we are trying to calculate these things and matrix, what will happen is, it will based on the different hidden layers. This hidden layer will have a Z1. Let's say this will have Z2, and this will have Z3. All this will be going further again into different neurons. Again, they will have their outputs, and that final output will be again going from the activation function, right? The final whatever output is there, and on the basis of that, we'll getting a Y hat, and then we are again calculating the Y loss, and again calculating the new weights, like for same formula, old weight minus new into multiplied by the weights. And for that purpose, we are trying to go down if it's negative. Positive, let's say we are trying to increase, because this is the minima. It is positive when we will try to decrease. The same thing will happen. Let's clarify this one. Chain rule, okay. This is now important. What is chain rule? What is chain rule? I will try to explain briefly, then we'll try to go in detail, and I will try to calculate one example. So what is the chain rule? And then I guess at that time you guys will be able to understand what is happening in the chain rule. So in chain rule, what we are saying is, I'll try to keep it simple. I don't want to like go into much detail. Maybe people will get confused, because really for me, first time in trying to understand this thing, I got confused. I will try to make it in simple way, that what happening is here is, we understood that whenever I am calculating the weight, let's say here, weight 1, weight 2. For simplicity, I am just taking 3 weights, and these are going further, right? This is weight 4, this is weight 5, this is weight 6. Again, all these things are summing up, and then we are getting the output, right? One is activation, one is summing up. So when I am trying to calculate our loss, and the basis of the loss, we're trying to calculate new value. Let's say, and this is again going W4, W5, W6, and let's say it has one more neuron here. That output, right? That is output here. This is 5. This is 6. Okay. So what is happening is, we have this many 6 weights, and basis of this 6 weight, we are going to get the output, this final output. So whenever, let's say, when in for backward propagation, I'm going back, right? In both the directions, I'm going back and try to update these weights. That is why I have to update the weights. I have to update these weights. Why I have to update the weights? Because I'm not getting my desired result So I have to optimize these weights. That is my main aim, right? So what happening is whenever I try to calculate this W4, it will be simple because for W4 it is the last layer, and then it is going into the, let's say that is going into the let's say output node. So for that purpose, that is simple. W4 new weight will be W4 old. Let me write the formula, then we can try to bifurcate further into the loss of W4. This part is clear, I think, for us, right? Now I am trying. This is learning rate. This is loss with respect to weight. So what happening is here, if I'm trying to calculate this weight, at that time it's okay. This is the formula I can directly do. Even if I go for 5, it's okay. For 6, it's okay. But when I'm trying to update, let's say weight 1 in this case. Since weight 1, it also depend on this weight, right? Depend on this weight 4 and the output which is giving here. This final output is, let's say, O3. This is O3 and this is weight 4. And this is weight 1. Okay. So what I can understand is when I'm going backward, first I will have output O3, and this O3 is coming from the weight W4, and this O3 and W4 all depend on the weight. So when I tried to update this one for W4, it was simple. When I'm going for the W1, what I have to do is I've written for W4 like this, and for W1 I can write for simplicity purpose, first overall broad equation that W1 new weight. This simple, I'm trying to just put in a simple formula first, then we'll try to make it more complex. Okay. It will be depending on what? Old weight, right? W1 old minus learning rate into differentiation slope with respect to the W1. So what I can see is this my entire product is depend on what? W4 and W3. So I can rewrite this equation again. Simply what I'm trying to do is, if this is a high level, then I'm trying to bifurcate them and try to reach to this level. So this part can be again rewritten. This part we trying to introduce this part. This W1 derivative consists of these parts also. So we can bifurcate them and try to write this like using the chain rule. Because if I'm writing like this, especially here, what I'm interested in loss function, derivative of the loss function with respect to W1. So derivative of the loss function can also depend on the what? Depending on the weight 4 and weight 3. And weight 4 depends on weight 3, right? So I can write this same thing as loss divided by can we calculate loss from the backward propagation? Also, both forward propagation they were the same. No, guys, I think you're trying to get in different way. The forward propagation, we are not calculating loss, right? We're just trying to predict. In backward propagation only, we first calculate the loss, and the basis of the loss in backward propagation, we are trying to calculate weights only. Try and understand the difference. This whatever weights are there, na, we are trying to calculate these weights in the backward propagation. That's it. We are not calculating again loss. Loss is calculated. That's why we are going back. There is a loss, right? Huge loss. That's why we have to back propagate in order to understand what are my optimal values for the weights. That is how the concept is, guys. Try and understand this way. Don't get confused. I know some things may be confusing, but try to understand. So what is our main aim? We first went to the forward propagation right from here to here, and we try to predict the value. Let's say prediction was y hat, right? Whatever a combination was there, we predicted y hat become 1, but actual value was 0. So there is a difference. So that difference is called as loss. We know this loss using the loss functions we calculated. Now I reduce the loss. That is my main aim. What I have to do is I have to reduce the loss. For that purpose, what I need an optimal value of all these weights. For that, calculating the values only, we are doing this optimizer and using all this back propagation. That is the main difference, guys. Okay. I hope I answered this question correctly to you and you are able to understand this thing. I understand when I'm talking about the weight one is written simply as weight, old weight minus the learning rate multiplied by the derivative of that loss function with respect to that weight. But that weight one is dependent on the weight 4 and the weight 3. So for simple mathematics, which we try to learn, whenever I am trying to further divide any term, what we can do is, we can write dl by dw like this one. When I'm trying to multiply and divide the same term, there will be no difference. This simple rule we'll learn in mathematics, right? When learning 10th and 12th. So same thing, what I can write is as dl by dw, dl by dw4 multiply by dw4 double by dw1, right? So if I cancel out this thing, again, it will come back to same thing, dl by dw, correct? So now I'm trying to consider now W4, but now W4 is also dependent on output 3. So what I will do is, I can rewrite this again by forget. Again, I can go ahead and what we can do, we can go ahead and again bifurcate it further or divide it further. So how it will look like, I'll try it again, clear everything. So I'll write my simple formula here for simplicity, dl by dw1 is equal to, this is mu v v1 old minus. I know, guys, it sometimes is confusing, but try to understand this concept is super important, because using the chain rule only, we are trying to update going forward from layer to layer and update the things. But try to understand. I will try to make it very simple. Just you have to try to understand that whatever weights, let's say I'm calculating this weight will be depending on the previous weights, right? Because we are not going forward, we are coming back, right? We reached here till prediction by this process. We reached to the prediction. Now what I am doing is, in backward propagation, I am going back again, layer by layer. Layer by layer, I am going back again. That's what I'm doing. This is back and this is forward, right? And going back, what I'm trying to do is, while going back, I'm trying to take the derivative of the loss. And why we take the derivative, we understood everything. By taking the derivative, we can reach to the minima point, because we have to reduce the weights and everything. This we understood, positive, negative side. And this is the 0 point we trying to understand. This is the loss trying to reduce. And these are the 3 dimensions. And this is my weight and bias. Everything we try to understand. That's why for the purpose, I have to take the derivative of the loss. That's what we try to understand. Now, while going back, if I encounter first weight, let's say here, this is my first weight. It is simple, because prior to that, there is nothing, no terms is no node is available. That's why I can directly calculate using this formula, right? What is the formula? That whatever old weight is there minus learning rate into derivative of loss function with respect to that weight, right? That we try to understand. Now, when we are going backward one more step, at that time it is trying to become complex. How it is complex? What I said is, this particular term W1 depends on what? If this is W1, this is depends on, let's say this was 4, and this 4 depends on what? Output. This output, right? Let's say this is output 3. So I'm trying to form a chain, guys. Try to understand that. I'm trying to form a chain. If I'm trying to form a chain, that is called a chain rule. So if I have to calculate this, I cannot break this chain, right? I have to consider both the terms, O3, W4, then only I will be able to reach to W1. That's what I'm trying to simply do in terms of the mathematical equation. Try and understand in a simple way. See, if I want to jump from P1, right, to W1, I have to take one path. I cannot directly go this way. like jumping from here to here. I have to take one path. One path will be this way. On another path will be like, try to draw on red line. Another path will be this way. Correct. So for that purpose, in path, whatever nodes are coming, we try to sum them. We're trying to sum or multiply them and try to consider their value. Then only we can reach to W destination. Simple. So we are trying to calculate the chains, right? We are going through the chains. That's why it is called a chain rule. That is a simple logic we have to understand. So what I'm trying to say is when I'm calculating the W1 is calculated how it is a old weight minus learning rate into derivative of the loss function with the weight. These terms again depends on what? W4 and W3. So I will try to just by let's say expand that term in second way. How I can expand that is derivative of loss with respect to derivative of weight 1 can be rewritten as, if I try to multiply and divide this term by the same term, then there will be no difference in the value. This we learn in 11, 12. So same thing I'm trying to do here. Okay. So whenever I'm trying to say that I have to write DL by DW1, but I can write the DL by DW1 in this way, DL by DW4 again divide by W4 multiply by W4, okay, and then again W1. So if I cancel this term, then it will, I will again come back to the same formula where I started. So simply again what I will do is, again W4 is dependent on O3. So I will try to bifurcate further. So how I can write is DW1 DW divided by W4 multiply by W4 divided by O3 multiplied by again derivative of O3 divided by derivative of W1. Getting, guys? I will try to write. I try to further bifurcate it. I have to try to write it again in darker line. So what will be my final equation now? DL by DW1. This derivative will be consisting of what? DL by W4 multiplied by DW4 divided by D output 3 again multiplied by D output 3 again divided by weight 1. So in between whatever terms I have introduced, these are the terms, because these are the paths we have to take. If P is trying to reach to W, I have to consider O3, then W4, then I can reach to W1. So that's what I'm trying to introduce in the derivative. That is called a chain rule, guys. Try and understand. Clear now? Simple way. What is chain rule? That's how the connection is there. If I am trying to update the weight W1, I have to also consider the weight W4 and output this, and I have to bring those in the loss function, calculation of the loss function, and then only I can calculate the new weight, which is again, we have seen here formula. That is the formula, right? Clear, guys? I guess everyone is now able to understand what is chain rule. So or you can say when I'm trying to calculate the things W1 again, or this is now just, guys, one step now. I can do further more complication. How I can do is, try understand now. If everyone is clear now, so I can go to a level 2 of complication. What I can do is, I erase some of the things here. I tell you the second part. This is not done, guys, yet. Chain rule. This is just the part 1. See the part 2 now. So what is happening here is, so I told you guys that in order to reach W1, I have to consider W4 and WO3, this path. But this prediction is also taking this path, right? Where I have this. This is W5, let's say. I will try to make it brighter for you guys. Part 1 is clear. Now part 2, try and understand part 2. Okay, this is W5. When I am saying, now what I am to do, I just saw one permutation. If I want to reach to W1, I can go by this path O3, W4 and reach W1. Now there is also another path available, right? In order to reach W1, that is going from, right? This going starting from the prediction P, going to W5, and from 5, you can go to W1, right? So further, what I can do is, I can add these terms also. This weight 5 and output 3. This is output 3, right? O3, and which is giving us the prediction, right? Try to write here prediction. So I have to add this remaining part also, right? Remaining part, what was the remaining part? D5, W5 and O3. So similar thing will happen again. What will happen is dW by D5 multiplied by D5 divided by DO3, and again multiplied by DO3 divided by DW1. Same thing, but for this path. Then it's complete, guys. Chain rule. Understood? Or complex? Or you guys got confused? Just ping me quickly that you understood the chain rule. Chain rule, what simply we're trying to do is, what we're doing is trying to go from P to W1. I can take either path 1. This is one way 1, and I can take way 2. So what I have to do is I have to combine way 1 and way 2. This will give me only combine effect for reaching to W1. That's what I did. Yes, guys, you are clear. You are really clear because you guys are super genius. So for me, but when I try to understand this chain rule, I went crazy that what is happening, because there are lot many derivatives happening here with respect to the weight, and I got lost in between. But I am glad that you guys are able to understand, and I am able to make you guys understand. Really amazing thing that you guys understood very well this thing. So try and understand. Just to summarize, what I am trying to do is, when I am trying to understand that how I can update the weight 1, let's make it more brighter. This is weight 1. When I'm trying to update this weight number 1, I have to take the combined effect, right? Combined effect of W4 and O3 plus the second one, which was W5 and the O3 again itself. So if I try to add, when I am talking about the derivative of loss function with respect to weight 1, this weight can be further bifurcated into these many derivatives, whatever we are written in the bottom. So that consists of the entire calculation. Then only basis of this calculation, I can calculate the new weight. That was the simple thing we trying to understand by making the terms complex. Okay, clear? I hope you guys understood this topic. Just keep on pinging me that you understood this topic. Meanwhile, I can go ahead. I know it's a little bit late now. We have 15 minutes left, but still in 15 minutes, we can cover some simple topic now. I thought I will try to show you guys and build one artificial neural network, but that's not an, let's say, rocket science. We can do it first thing in the tomorrow morning, but try to understand such super important concept, which is called as vanishing gradient descent and the dropout layer. So this layer, these things, complex terms we understood, right? Same explanation I am given here. Same explanation is given here. So you guys can, whenever you go back and try to follow the things, you try to understand. Okay. So first we try to do is what? We try to update the weight 1 here at the level 3. Sorry. So this was the weight we're trying to update here. So for that purpose, I took the loss of output 3 and weight 1. And then we further went ahead. And then further we wanted to calculate this one. For that time, we have to calculate this. At that time, if you have to calculate this one, we have to calculate the O21 as well as O30, O21, 21, 31, and plus these weights. So that was the combine effect we were trying to take. That explanation also I have given here. So how like we are adding this additional term here, how we are coming with this additional term when I am trying to update the things. Maybe when you guys will go back at that time, you'll try to understand. But I think you guys understood that whenever I'm taking this path back or this path back, whatever destination I'm trying to reach, whatever the nodes will come, I have to take the loss derivative, addition of this derivative of the loss function with respect to that, whether it is a weight or output or combination of the weights and outputs. I have to take and combine them, then only you can calculate the weight one. When I try to calculate weight one, I have to calculate output 11 also, weight 11 also, and output 21 also, weight also, and I have to combinely write the things, and then only my model will be able to calculate, and that is called a chain rule. So now how the things is happening is, how the entire process look like. So when I am trying to give a picture, right, picture of the dog, let's say, then try to go through a neural network, this inputs multiplied by weights, summation of weights and inputs, then passing through the activation function, right, coming as output, and then whether based on the threshold it will give you whether it is cat or dog or whatever it is. If it's a cat and actually it is dog, that means there is a huge difference. So our gradient descent start working now, optimizer, and again we go back, try to update the weights, right, updating the weights, and again we have to start again from the first step, like take multiply inputs, weights, multiply inputs divided by the weights plus activation function, then again predict. And this is for simple layer, there will be multiple layers, so that many times the calculation will happening. But this is how the actual it will try to fit into the bigger picture, like whenever we're trying to do the back propagation for propagation, or how entire cycle will work. So that's why when we went into the deeper level, then try to imagine this deeper level, try to connect the dot with the higher level picture, that how the process is happening. Whenever we are trying to give any image or try to identify a binary class, like whether it's a dog or cat or something like that, that's where you can fit in. So that's why I told you guys that why weights are important, why bias is important, how the activation function is playing the role here. And then on the basis of that, how the optimizer is calculating the weights, and we are doing the back propagation. And similar thing will happen for the complex topics. And once, see what will happen is also, once we get it, that was previous case when we are not getting the desired result. What if we get a desired result? At that time, what will happen is the network will try to freeze that weights. Okay, it will try to freeze that weight, whatever weights which we were able to get the prediction correctly, and then on the basis of that weights and everything, we'll try to bring the test data. Test data will be introduced, and on the basis of the test data, we'll try to predict the things, and then we'll try to check the accuracy, how it is performing. Till now, here we were only on the training phase, and in the training accuracy, we're trying to check. And on the training accuracy only, we were doing back propagation, right? Back propagation was happening. If I try to fit into the testing level, when we are able to predict accurately, we are trying to achieve certain sort of accuracy, let's say 97% or something like that, 98%. Then this weights, whatever weights, because everything in the neural network works on what? Weights and biases. So once I know weights and biases, exact value of the weights and biases, I don't need even this neural network. I can directly create new neural network. I can take that value and I can start doing the predictions. So that is the main thing. Once you freeze this weight, means what? You take that values will be stored in something like that, let's say H5 or some kind of let's say format, and then maybe whatever iteration you are doing at that time, you try to take a checkpoints, or for that checkpoints it will try to freeze the weights. And once you know the weights, you can directly input that weights, or you can use that similar model that try to load that model, and then you do the prediction, and it will able to help you with the correct accuracy. So try understand that. I will quickly try to take this concept. I will not go in detail maybe, but I will not try to rush even. We still got 10 minutes. So it's a good amount of time to discuss the vanishing gradient descent. Okay. What do you mean by vanishing gradient descent is attendance link is shared by Amar, guys. Okay. And feedback link also. Don't worry about it. So what is the main thing here? What is the issue with the back propagation that this vanishing gradient happening? So main thing is whenever we are trying to use this back propagation, we're trying to calculate the derivatives. At that time, initially, every neuron that participated in this calculation output, right, associated with cost function, try to calculate the cost, and when we try to calculate the cost, we bring the optimizer, and by optimizer, we're trying to reduce the error, and we are trying to estimate the new weights. When we trying these things multiple times, at times what happens is when we try to multiply these things, when we try to do this derivative multiple times, at times what happens is my derivative or loss functions derivative with respect to weights try to become very small. It reduces to very small number, right? Once the problem happens, how the problem start happening is whenever I am trying to take this gradient, right, this loss derivative with respect to the weights, at a certain level or certain epoch, what will happen is this value of this derivative will become so small, and what will happen, I will try to tell you, if this value is become very small, when I am trying to predict the new weight, when I am trying to predict the new weight, how the new weight is calculated, weight new equal to weight old beta into derivative, obviously, with the weight. And my influencing factor over here to change the weight, right, is derivative. If it is positive or negative, on the basis of that, I am trying to sum in the old weight, or I am trying to remove from the old weight. So if this value become very negligible, right, or very small, so divide by the learning rate again small, it will be like something around 0.01 or something like that. And this my old weight is, let's say 5. 5 multiplied by this is like what? Very small value will be. Again, it will be very small value. So my new weight will be very small. And with this new weight, I'm just trying to give you guys overview, right? We'll try to understand in better way. But what I'm trying to tell you that vanishing gradient problem happens since when we try to take the multiple times the derivative of the loss function with the weights, at that time, at a certain level, what will happen is it will reach to a very small value. And if I trying to input that small value into this formula of calculating the weight, then my old weight and my new weight maybe become equal. So if my new weight and old weight become equal, right? So how my neural network will learn? Because I am not updating the weights. If I'm not updating weight, if I'm trying to keep them same, then nothing will happen, right? Nothing will change, and my model will not be able to work. Not able to work means it not be able to reduce the loss. If I'm not able to reduce loss, how will I perform with higher accuracy, right? So like again, it is associated with accuracy. So that is the main concept, guys, behind the vanishing gradient descent. Vanishing gradient descent happens when whatever derivative I have to track, it become very small, or the weight derivatives becomes very small. This derivative function, derivative of the loss with respect to weight become very small amount of time, right? Very small values, so that the old weight and new weight doesn't make any much changes, hardly make any changes. So if I am not making any significant changes in my weights, so my model will not be able to understand. That means I am not trying to optimize it in better way. Optimization is not happening, and my loss is not getting reduced then. So that is the simple concept behind the vanishing gradient descent, guys. So I will not start probably today. I'll try to take these things first thing in the morning. So we'll in a couple of minutes, we'll try to understand how these things is happening from mathematical point of view, and what is the problem with the sigmoid function. And then we try to create our own neural network, and we'll try to solve one classification problem using that neural network. And I'll to make you guys code walkthrough for that purpose. And I'll to what I will do is I can pick one example on Kaggle and one example maybe on the Colab. I will try to do one with image and one with the normal numerical data set, maybe with the neural network. So still some concept is remaining, dropout layer and the exploding gradient descent and this one. Then we'll be done, guys. We'll be able to finish this entire things. I hope, guys, whatever topics we discussed today, you guys were able to follow it up, and you found it very interesting that how the weights are getting updated, what is happening in back propagation. So hope you guys enjoyed this session. Just quickly ping me your feedbacks, like how you felt about today's session, and then maybe tomorrow we can again start with the new session. We'll try to go into further creating the neural networks. Okay, guys, quickly ping me the feedback, like, and attendance is already shared with you guys. Attendance link and feedback, guys, and any feedback, whatever you wish to tell me, you can just quickly ping me in the chat box. I try to make it very simple. Whenever first time I try to look at this concept, I lost in between the gradient, loss function, weights, and some outputs. But I hope I am able to explain you guys in the simple terms, the complex terms. So just quickly give me somewhat more pings, guys, what you felt about the session. So accordingly, we can again prepare further. If you want, you can ask any query, guys. We still got like a couple of minutes. So before we close this session. Yes, sir. Feedback form is already, Amar has already shared the link. Yeah, thank you, Kavita ma'am. You understood. Excellent. Thank you. Thank you, Vandana ma'am, for your comment. Anyone else, guys, would like to add anything? Amar has already shared, guys, the link. Maybe Amar, you can just paste it again in the common chat box. Yes, Amar has again given it to everyone in the chat box. The same link for the feedback and the attendance. Please fill it. Okay, thanks for your comment, guys. Keep on pinging. If you guys want to ask anything particularly today's topic, just ping me quickly. We got a couple of minutes before we close this session. If you want, or if anything is not clear with you guys, or if you felt that I should have asked this question, just couple of more minutes, and then I will be able to answer you this. Thank you, guys. It's really motivating if you guys keep on giving this kind of feedback. It's really motivating this. But the main aim why we are trying to take this session is that you guys able to understand the things and follow it. So because I will be giving you assignment, guys, you have to prepare your neural network, and then you have to come up with this hybrid DL models tomorrow. Yes, we'll discuss about the hybrid DL models. Yes. Any question, guys, apart from that about the topic, whatever we discussed, like back propagation, optimizer, how the training is happening over here, how the weights are getting calculated, how the gradient descent is even working, what is chain rule, you guys are able to follow. Back propagation is used to modify the weights, so to get the accurate prediction. Yes, ma'am. Correct, Supriya. Correct understanding. Anything else, guys? Just quickly ping me. Otherwise, we can close this session. Just give me confirmation, guys, so we can close the session then. Yeah. We'll cover dropout tomorrow, guys. Dropout, exploding gradient, exploding descent problem. What do you mean by exploding gradient descent, and what do you mean by vanishing gradient problem, excluding gradient problem. That will cover tomorrow in detail. We try to understand why it is happening and what is the main reason behind it, and then we'll try to create our own neural network architecture tomorrow. All right, guys. Then, if no further questions, then Amar, you can go ahead and close the session. See you guys then tomorrow. Thank you very much.
Yeah, sure. Thank you.
Thanks, guys. Again, see you tomorrow.